If we're searching for the fundamental particles in our universe, then we seem to have pretty much succeeded now that we know about leptons and quarks. But I think there's still some questions. Take beta radiation, for example. A neutron is changing into a proton. Now that we understand that neutrons and protons are both made up of quarks, we can dig into that a little bit deeper and we can try to understand what is going on in terms of the quark compositions. And what does that mean in terms of fundamental particles? Now, most of this lesson video is going to be off the syllabus, but it's a fascinating backstory and it's going to help you to understand the beta decay in a lot more detail. So if you really don't want to do that, then skip to the end and I'm going to summarize what it is you actually need to know. But if you're up for it, let's get on with that backstory. We're going to start way beyond the syllabus by looking at forces. Fundamental forces, kind of. Now, as a physics student, you'll be familiar with all sorts of forces. There's gravitational force, electrostatic force, magnetic force, friction, air resistance, the normal reaction force, tension, pushes and pulls. But to a particle physicist, there are only 4 forces, and 2 of those only exist within the nucleus. Let's start with gravity. It acts on masses and it is always attractive. It's extremely weak with a relative strength of 6 × 10 to the minus 39, but it has an infinite range. Now that might surprise you. Gravity seems pretty strong to us, but that's only because we're really small and we're standing on top of this absolutely massive Earth. Okay, it's actually quite a weak force. Next is the electromagnetic force. Now electrostatic and magnetic forces fall under this obviously, but so do things like friction and the normal reaction force and tension. Now if you think about it, when you stand on the floor, you don't really touch it. The nuclei in your foot get very close to the nuclei in the floor, but they won't actually touch. They will repel. And that is the electromagnetic force. It's way stronger than the force due to gravity, but still only has a relative strength of 7 × 10 to the minus 3. It has infinite range as well though. Now the force all others are measured against is the strong nuclear force. It only acts in the nucleus and it's strong. It has a relative strength of 1 and a range of 10 to the minus 15 meters. That's about the diameter of a medium-sized nucleus. It holds the nucleus together, but it doesn't affect the leptons at all, the electrons. Lastly, there is the weak nuclear force. It also only acts in the nucleus, and this one has an even smaller range of 10 to the minus 18 meters. That's 0.1% of the diameter of a proton. And it is weak, with a relative strength of 10 to the minus 6. Here are some bonus fun facts. The strong force repels when particles are really close, but attracts when they are further apart. And people don't like saying weak force, they usually prefer weak interaction. The weirdest fun fact though is that all of these forces occur through exchange particles. Gravity has the graviton. Strong has the gluon, because it glues things together. Weak has W plus and W minus amongst others. And electromagnetic has, would you believe, photons. Now we're going to look into the weak interaction now because it is responsible for the decay of subatomic particles. Let's start by understanding how these exchange particles can provide a force. Oh, and before I go in, I really want to make it clear, you don't need to understand what's going on with the weaker interaction for CIE AS Physics, but I think it's fascinating, and I think it's going to help you to understand how beta decay is actually working. So, exchange particles, what are they? And how can we use them to explain a repulsive force? Well, imagine you are standing on a skateboard. You have a friend who is standing on another skateboard, maybe 2 meters away from you. So that means you can't reach one another to touch, not even with a stick. So how could you push your friend away from you? It's quite a tough question. I'm going to give you a big clue in a moment, so if you're still thinking, pause. Think about momentum. Alright, so you could throw a bowling ball to your friend. Alright, how's that going to work? Again, I want you to describe in as much detail as you can the motion of you and your friend when you throw the bowling ball and your friend catches it. Give this a try. Hit pause. Get the detail about momentum in. Okay, so at the start your momentum is 0. When you throw the ball towards your friend, the total momentum must stay 0. So you are going to have to roll backwards on your skateboard. Your friend starts off with 0 momentum as well, but the ball, when it arrives, has got non-zero momentum, so when they catch the ball, they must roll backwards. You have repelled one another. In this analogy, the bowling ball was an exchange particle. It was exchanged between 2 friends. So, an exchange particle is a particle that is exchanged between 2 other particles and results in a force. And curiously, that exchange particle did not exist before the interaction. It was created out of nothing, exchanged, and then it went away again. Actually, okay, alright, more precisely, it was created from energy, exchange, then the energy returned as it disappeared again. In quantum physics, particles like this can be spontaneously created from energy, but only as matter-antimatter pairs. So, that explains repulsion, but what about attraction? Can you now try to imagine how exchange particles could cause attraction? Okay, go on, have a think. Okay, so here's one way of doing it. You and your friends stand facing away from one another on your skateboards. Instead of a bowling ball, you create a boomerang out of energy. Throw the boomerang away from you and your friend. Now, momentum will cause you to roll gently towards your friend at this point. As the boomerang spins round past you both, then round again for your friend to catch it. And they roll gently towards you. And that is attraction. You've moved closer together. Now, I'm not suggesting that particles are throwing little boomerangs around, but what I want from this is that you accept that the idea is possible. It's possible for exchange particles to be the cause of both repulsive and attractive forces. Now, let's finally look at beta radiation. In beta minus decay, a neutron changes into a proton and emits an electron. Now remember, this is nuclear physics, so that electron did not exist before it's been created. Let's check that equation. n goes to p plus e. Considering charge, we have 0 plus 1e minus 1e. So that's balanced. Baryon number 1, 1, 0. Okay. Strangeness 0, 0, 0. Yep. Lepton number 0, 0, 1. So that's not balanced. To balance the equation, and it does have to be balanced, we need to put a lepton on this side. Now it can't be an electron because charge is already balanced, but a neutrino is a lepton, and a neutrino has a charge of 0. It's neutral. So I can balance the equation like so. Okay, put a neutrino over on the left, balanced. Now, this is a Feynman diagram. It's a wonderful way to describe particle interactions that, once again, is not on your syllabus. Reading it from the bottom, a down quark interacts with a neutrino through the weak interaction. In other words, they exchange a W- exchange particle, and this causes the down quark to change into an up quark, and the neutrino to change into an electron. That works, but it doesn't really look like spontaneous decay. We needed this neutrino to trigger things to come along. So there is a second way to balance that equation. Instead of putting a lepton on this side like I did first time, let's instead put an anti-lepton on the other side. So n goes to p plus e plus nu bar. Nu is the symbol for a neutrino, and that bar on top of the neutrino shows that it is an anti-neutrino. And here's a diagram to illustrate what is happening. Now it's the creation of this neutrino, so we now have 3 products that are going to share the energy release, and that means a beta particle can have any value of energy, unlike an alpha particle. Finally, a proton can decay as well. In this case, the proton creates a W+ exchange particle as it changes to a neutron, which leads to an anti-electron, also known as a positron, and a neutrino. Inside, a down quark is changing to an up quark, and the other 2 quarks are not involved. And that's it. So, what do you actually really need to know? All you really need from this lesson video are the quark equations for beta and beta plus decay. So up, up, down goes to up, down, down plus E plus nu bar. And up, down, down goes to up, up, down plus E bar plus nu. You should also know that electrons and neutrinos are members of the same family, which we call leptons, and that leptons and quarks are considered to be fundamental particles. The positron is the antiparticle of the electron, which means they have the same mass but opposite charge. Everything else was just for fun, but I hope you're trying to understand at least a little bit of it.